let's do it. Okay, so this class is going to have a look at the logarithms portion of exponentials and logarithms. So it'll be bulk focused on the logarithm stuff. We will eventually go back and look at a little bit of exponentials, because what you'll start to see in this section, or maybe you've already seen it, but logarithms and exponentials play together quite a lot. There's often going to be a relationship between a logarithm and its equivalent exponential, and vice versa. Okay, so what is a logarithm? Well, as I said, it is related to an equivalent exponential. In fact, you can take any exponential statement with any exponential equation and rewrite it as an equivalent logarithmic equation. So the way to think about this is you're essentially just replacing all the terms in the exponential statement into different spots in the logarithm statement. So what we know about exponentials is that they are some form of y equals a to the power of x, where a is the base and x is the exponent. The thing with logarithms is the x is now going to be the subject of the function. So instead of it being exponentially increasing, we now have what is basically logarithmically increasing. That is that as x gets larger, the rate at which it's increasing starts to slow over time. So like, for instance, the green line here is exponential, the blue line here is logarithmic. Right? As x is getting bigger, it's still increasing over time, but the rate at which it's increasing is slowing and slowing. It's plateauing over time. But okay, so that's the reason why logarithms exist. As for the conversion, I've used the same terms in both of these statements here. All you're doing is putting the a in the base of the logarithm. So the notation there is log base and then bracket. The base of the logarithm is exactly the same as the base of the exponential. The index is the subject of the logarithm equation, and whatever the subject was of the exponential goes in the brackets of the logarithm. This is kind of just something you have to have memorized as for how these things convert into each other, because you don't really get this on your formula sheet, and these do show up a lot in tech-free, so it's just going to be something you do several times over. To see an example, you have this statement here, 6 equals 4 to the power of x. You could rearrange that into an equivalent logarithmic expression to now solve for x. So what this does is it gives you a way of solving exponentials that otherwise have no nice solution. Like 6 being equal to 4 to the power of x, if we think back to when we were doing our equating exponents or other methods for solving exponentials, there's really not much to be done here, right? Like, we can't get 6 down to a base of 4, or even a base of 2 for that matter, so we can't directly compare bases and exponents, and there's really nothing else to be done. So logarithms, one of its advantages is that because it gets the exponent on its own, you now have a tech-free way of getting a nice and succinct answer for what x would have to be to make this work. Now, this number here is just going to be some decimal that's infinitely extended. It's an irrational number, so it'll continue on forever. So this gives us a nice and neat way to write them in a tech-free way. It's not the historical reason for logarithms existing, at least I don't think so, but that's, as far as methods is concerned, that's what we're caring about for the relationship between exponentials and logarithms, which I've also detailed out here. So the more specific way to describe the relationship between a logarithm and the exponential is that they have an inverse relationship between them. I think you do inverses in Unit 1 and 2 and 3 and 4 as well, so this should be relevant to everyone. The way you solve inverses of any function is to start by swapping the location of the x and the y in the equation. Like, for instance, if you have y equals a to the power of x, you now have x equals a to the power of y. You're literally just replacing every x with y and every y with x. You'll do that for every inverse you ever do. And then after that, you then rearrange for y, thus obtaining the inverse of the function that you're trying to solve for. The reason why that's in the logarithm chapter specifically here is to show you that when you perform that on an exponential, you actually end up with an equivalent logarithm. They are inverse pairs of each other. So you have y equals a to the power of x. That becomes x equals a to the power of y. Now to get the y back on its own, because it's in that exponent spot, we now understand, oh, cool. If it's in the exponent, we have this little conversion that flips them. And so because it was in the exponent, we can get it down on its own by flipping to a logarithm. And so sure enough, we do exactly that. Y becomes on its own. The logarithm has been achieved. Graphically, that ends up looking like this. So any inverse is the reflection in the line y equals x. So we're not reflecting in any of the axes specifically. We're reflecting in this diagonal line. That's what any inverse is going to look like. And sure enough, we see that exactly happen with the logarithm. Any questions about what we've covered so far? Okay, so a bit more on notation. These are probably the only logarithms you'll ever come across for the most part. By far the most common is going to be the natural logarithm. That's when your logarithm has a base of e in it, e being Euler's number. It's very specific. It's like 2.7-ish. It's like pi in that it's an infinite irrational number. You'll often see it shortened to ln, natural log of x. This is what you'll see on your CAS. So I've got both of them here actually. So we'll start with looking at TI Inspire. If you want to hop over to the other camera, what you'll see somewhere on, if you're TI Inspire, will be you've got the log and you've got the ln. And what you'll notice is that the ln is the secondary function of the e to the power of x. That's once again highlighting the relationship between the fact that that's a logarithm with a base of e. And if it's on the other CAS, oh no, I'm going to have to turn it on. Let's see if it has battery. Yes. Okay. ln, right there. So that's the specific natural log, and again, it's right next to the e to the power of x. Yeah, that's just a bit on notation. It's not just like that in your CAS, it's also like that in some textbooks. Maybe the exam might do it as well, possibly. Anyway, back to the screen share bit. The other logarithm that's likely to come up, but oddly enough less commonly, is the so-called common logarithm. It has that name for a very different reason. That is just a logarithm with a base of 10. So it'll either be log 10 or with a capital L. It's pretty rare to come up, but this is just another notation for logarithms. The reason why it is called the common logarithm, by the way, is because our number system is base 10. That is to say we have 10 digits that we use for our numbers. Hence the reason for the common logarithm. That's where logarithms really had their roots in around the number systems as well as how you express data. That's another reason for them to exist, but that's sort of beyond the scope of what we look at, just more a bit of trivia. Okay, so just like we have index laws for exponentials, we also have logarithm laws for logarithms. These are actually the exact same thing, because if exponentials can be flipped to logarithms, what you're essentially seeing here is what those index laws now look like when everything's been converted to a logarithm. So some things worth pointing out just to help out. The log laws are only going to apply when logarithms have the same base, kind of like with the exponential, the index laws, right? You wouldn't be converting, you wouldn't be working with things that had different bases and combining them into each other. They have to have the same base to actually use any of these laws. The other thing worth pointing out, and this is not necessarily always true, but because you can have some workarounds, this is more so just to make life easier for yourself. If you see any coefficients at the front of your logarithm, try to rewrite it in a way where you don't have those coefficients. It's a very similar thing to when you're doing your index law stuff, right? Like if you had e to the power of x times 2e to the power of x, you now have to figure out how the coefficients play with each other, not just the powers, which that's a bit of an easier example. We have a lot more experience with working with index laws. When it comes to logarithms, because this is so much newer, then just working with basic like x squareds and stuff like that, it tends to get a bit confusing how those coefficients play with each other. So best off just try to rewrite it in a way where you don't have those coefficients. And as a bit of a sneak peek, you can do that with this law, but we'll get to that in a bit. First up, the so-called product law. Simply put, if you have two logarithms with the same base that are added together, you can replace that with one logarithm that has the product of both brackets in there, just multiplying them up together. This also works both ways. So if you just had some logarithm with something in the bracket, like let's say 9, for instance, you could split that up into a logarithm of 3 and 3, respectively, because 3 times 3 would get you 9. You can go one way, you can go the other way. It just depends on what you need for the scenario that you have. This will work for all the laws, and not just in logarithms, but also in literally any equation you ever get. They always work in some form of rearranged version of each other. Okay, quotient law, very similar. If you have subtraction, you get division. And the one that's probably a bit more unique is the power law. So essentially, if you have a coefficient at the front of your logarithm, what you can do is take that coefficient into the bracket of the logarithm as a power. Whatever that coefficient is becomes the power of the thing in the bracket. And again, that works backwards as well. So if you have a power in there and you don't want it in there, you can shove it out of the brackets by just doing exactly that, shoving it out. Those are the three things you look at the most. Anything to clarify about any of those, how they work? Cool. Because this is basically your fundamental algebra for this sort of thing. Similar things here, logarithm identities. They are similar in nature. Let's have a look. Basically, if you have the same base and bracket in a logarithm, that will always end up equaling 1. So this one comes up a fair bit when you're doing your simplification steps. So if you ever end up with like log 2 of 2, for instance, you wouldn't leave your answer as log 2 of 2. It can be simplified down to just 1. Whenever the base and bracket are identical, the logarithm is always 1. I have a bit of a proof statement in all of them. It's there not as a mandatory thing for you to know, but more so just in case you forget what these laws actually are. So if you have like, when you're doing your working out and you're like, I think this simplifies further, but I don't quite know what I need to do to actually achieve that. One of the things you can do generically for pretty much all of these laws to prove it is to just start out with the assumption and be like, okay, I think log a of a simplifies to something. I can't remember what it is though. So whatever that thing is, just call it y, x, whatever you want to call it. You start with that logarithm statement, convert it to an equivalent exponential statement. So again, this is going to require you to remember how those things flip over, but that's a skill you'll need anyway, so that should be fine. And when you look at this, you realize, oh shit, okay, y can only ever be 1, and so if y can only ever be 1, then log a of a can only ever be 1. That's just one example of proving one identity. You'll basically do the exact same thing to prove all the others as well. Start with the thing that you think can be simplified further, make it equal something, flip to a exponential, and then that exponential is usually easier to look at and understand. Very similar, if you have the bracket as 1, it doesn't matter what the base is, the logarithm will always equal 0. There's a similar proof here. Simply put, the index becomes 0, anything to the power of 0 becomes 1. If you have a negative in the bracket, you get a non-real solution. This really only matters for spec math kids. For methods, we don't really care whether it's non-real or just doesn't exist entirely. The reason why comes from, again, converting to the exponential form. And we discussed this earlier, which was there was no index that was possible to make a negative answer. There was no possible value of y that would turn this exponential into a negative number. I do detail one that can eventually show up, but again, this is spec stuff. And if your bracket is 0, you have what is considered an undefined solution. So undefined is different to non-real, but again, I just want to highlight that the differences there aren't particularly looked at in methods. The reason why this one's undefined specifically is because with non-real, you have an imaginary solution. That's in Specialand. With undefined, even in Spec, there's no actual solution to this. If you were to convert to the exponential form, you'd have an exponential that equals 0. But even just briefly, if we look at this, this exponential graph, it has an asymptote at 0. It never actually reaches 0. So we don't know what base would achieve 0. We could infer that what exponent? We could infer that x equals negative infinity would get us there eventually, but it only ever gets closer, never actually equals 0. And for that reason, we consider it to be undefined. So all this means is if you see that in your working out, you've either done something wrong or you just say there's no solution, undefined. If you have negatives in there, again, very similar thing. Either your solution's wrong or you, or that just flat out is your answer, no solution. I need to rewrite this. It's not niche anymore. I've seen a fair few uses of this. In mostly Saxon exams, what they'll do is they'll chuck a logarithm in the exponent of your exponential equation. Whenever you have that, it'll often be the case you'll be able to use this identity. Now, not always the case, but if it's in a question, it likely is. The key thing you're looking for is that the base of the exponential is the same as the base of the logarithm that's in that exponent spot. If you have that, nothing else matters. The solution is just whatever's inside the bracket. That whole thing simplifies down to just whatever's in this spot here. The proof here is a little bit stranger. You start with your supposition that log a of x is equal to something. You flip to the exponential form, and then you just say, well, y equals this anyway. So I'm just going to chuck that back in, and then you get there. There's no actual further analysis here. You just kind of grab this thing and chuck it back in. I've seen a fair few uses of this in Sax. Maybe we'll see it in the book, but I've definitely seen a few uses for making this one happen. Any questions as to how any of those work? I know I've got the proofs in there if you want to look at them, but yeah. Okay. This one is more niche. It has a use in the book. I don't believe it's required or has been required for anything in an exam before. So let's have a look. Any logarithm that you have can be converted into a logarithm with a different base, depending on what base you want. Now, in some arithmetic, you might want to... We talked earlier about the fact that the logarithm laws only work if you have the same base between them. So this might be something you consider to do, although I don't think it's ever really required as such. It just might be a nice thing that you think of to make the simplification steps easier. If you want, you could just memorize that. It details how you could start at one logarithm and end as a division of two separate logarithms. Essentially, the base of the logarithm will go into the bracket of this bottom one, the bracket of this goes into the bracket of the top, and then whatever base you want goes here. You get to choose what b is. So if you want to have that memorized, feel free. I don't have that memorized. I essentially go through and do the exact same steps in the proof that I was mentioning earlier, which is kind of why I brought it up, because you'll use a very similar technique to do this, which is you start with whatever logarithm you want to convert, flip it to an exponential, the equivalent exponential. What you do from here is kind of like how you can apply a root or a square on both sides of an equation. You can also apply a logarithm to both sides of the equation. And because we're doing the application of it to both sides, we can choose what we're doing, right? Kind of like how we can square, cube, power of 4, anything on both sides of the equation. We can choose the base of our logarithm. That base is going to be what you actually want it to be, which ideally would be one that actually matches something in the question that you're trying to simplify. So you just wrap both sides of this equation with logarithms. A to the y goes in the brackets of this log, x goes in the brackets of this log. From here, you do your log law stuff to get y back on its own. And the reason why is because we're trying to get this original logarithm written in terms of a different base. And because that original logarithm is called y, getting y on its own through the power law and then a simple division gets us to that formula that we're looking for. Y equals that, but y is also equal to our original logarithm, so hence our logarithm is equal to that division. Any questions on the procedure there? Cool. Yeah, there's a billion examples we can go through. There was no real need to put any specific in here. I have a full detailed set of solutions to, well, specifically the Unit 1 and 2 book. I don't know why I didn't do Unit 3, 4, but it's all the same stuff. If you don't have your Unit 1 and 2 book anymore, feel free to let me know. I'll drop a copy of it in there as well. That's if you want to look at those anyway. Do we want to take a break and start doing a few practice questions on these, or should I keep lecturing? Any preferences? Sure. Okay. More talking. Okay, cool. So I kind of mentioned this already. The logarithm is the inverse of the exponential. I feel like for most people, the shape of the exponential is a bit more natural. People think about things as increasing exponentially. Usually your first introduction to this is probably going to be something like economics, how money increases at an exponential rate, it compounds onto itself. Logarithmic growth is typically a lot less understood, unless you guys were listening to the news when COVID was a thing, because they would plot the cases on a logarithmic graph. So it made it look like it was significantly more contained than it was, because you can see how the logarithm, as x gets bigger, the y values don't increase as much over time. What they were essentially doing was, one, condensing all the data down onto a nice and easy to see page, but it also kind of hid the magnitude of the numbers you were seeing. But anyway, the logarithm, just like the exponential, also has this new figure, which is the base in there that also determines the shape. If you're ever trying to figure out what the shape is, just think about the equivalent exponential and then flip in the line y equals x. So if you consider the change in base, all you're really doing is changing the magnitude of how it curves. It doesn't really do too much to the graph, kind of like how the exponential base doesn't do too much to the graph, unless it's between 0 and 1, in which case, just like the exponential, it'll flip. Now, exponential is the green one there. It flips across to y. Because you're flipping in the line y equals x, this dotted line, instead of flipping in the y, the logarithm flips in the x instead. So it starts at the top and then shoots to the bottom right. Again, these aren't necessarily super intuitive, so if you're happy enough with your exponential stuff, picture that one first and then imagine what that would look like flipped, which is why I have these both overlaid on each other. Dilation factors work the same way as always. The number at the front will scale it across along the y-axis, or from the x, however you want to pronounce it. Dilation factors in there are along the x or from the y. Keep in mind again that dilation factors along the x or from the y appear as divisions. So this one here would be a dilation factor of 3, and this one here would be a dilation factor of a third, because it's got to show up in that division spot. But that's more of a transformations theory thing. Reflections, you can have both reflections in the logarithm. Again, keep in mind that because we have different bases, the base of the logarithm is another way to flip across the x. So you essentially have not only this one to flip in the x, but also the base as well. So keep that in mind when you're working with these things. That being said, you pretty much never see a logarithm with a base between 0 and 1. It's very likely to be the natural log, log e, or maybe log 10, none of which are between 0 and 1. Here's another reflection. Again, these work the same way as always. If the negative is on the x specifically, you flip horizontally. You flip across the y. Translations, again, this works the same as any other function. Your h determines your horizontal translation, your c determines your vertical translation. Negative will shift it right and positive will shift it left, for h, for the horizontal anyway. The key thing to watch out for here is kind of like how an exponential has an asymptote, so too does a logarithm. In fact, it will always be the same as the equivalent exponential asymptote. So this one has an asymptote at x equals 2. If you flip this to the exponential statement, that exponential will have an asymptote at y equals 2. And that's actually a key thing to watch out for, because a couple of times you'll get the logarithm or the exponential and then have to infer things about the equivalent other component of that. So being able to look at these things on the graph and be like, yep, that has x equals 2, so therefore the y equals 2 should be the equivalent for the exponential. Same goes for all inverses, actually. Any x information on one graph becomes the y information on the other graph. This is just a shift left. Again, plus for x always goes left. And vertical translations do next to nothing for the logarithm. Yes, it obviously does something, but as far as your drawing of the graph, it doesn't really influence anything beyond the actual math that comes out for your axes, intercepts, and such. So solving them is basically identical to solving the exponentials. You want to have your asymptote, which in this case is given by the horizontal translation rather than the vertical. And then your x and y intercepts are both x equals 0 and y equals 0. To get the x-intercept, you'll often have to flip to an exponential form. In simpler cases, that exponential form will condense down into just a nice and neat number, whereas the y-intercept is always pretty much just going to stay as a logarithm, usually. Yeah. Here's our procedure for following things, very similar to the exponential. Before I get into that, was there anything individually in there worth clarifying further? Yeah, and if there's anything even further back as well you want me to retouch on, feel free to let me know, either by message, unmute, whatever you like. Okay, example. I've given a nice and nasty one just to show you that this works for all logarithms, not just the simpler ones. First thing you want to do for any sketching of any function is make it look like it doesn't look like shit, right? Make sure you can see all of the key features that matter in it. So in this case, I'll be expanding this out so you can clearly see the vertical translation here and the dilation, the negative. This one's still a bit hidden. We do actually really care about that horizontal translation, so we're going to do a step further and take any coefficients off of the x. That's something you'll want to do not just for logarithms, but for any function, so you can more clearly see the true horizontal translation. That one mattered a lot. We had a +5, so that meant that our asymptote is now x equals -5. As for the overall shape, we look at the base and we look at the any reflections that exist. So natural log is a base of e, which is roughly 2.7. So our basic logarithm is this sort of shape, right? Any base greater than 1 will start from the bottom and go to the top right. That's what it starts out as. We did have a negative sign in ours. We had a negative at the front, which is always a flip in the x, right? And so instead of going up and right, it's now going down and right instead. It's flipped in the x. You can draw a rough sketch of this just to get an idea of if you even bother looking for x and y intercepts, or maybe just x intercepts. The logarithm will always have an x-intercept. It may not have a y-intercept. Like if you see here, these ones have an asymptote at a y. They don't actually touch y. which is probably worth pointing out actually. If they don't always have a y-intercept, sometimes you'll be able to prove it where the bracket of the logarithm becomes 0 or a negative number. Remember, both of those are failure conditions for the logarithm, which was negatives means it's not real, 0 means it was undefined. So if you get those in your solution, it may not be the case that you've done something wrong. It might just be the case that you don't have a y-intercept. But this one clearly does, so we'll find it. Okay, x equals 0 and y equals 0 for the x-intercepts. For the x-intercept, so what you want to do essentially is get the logarithm on its own. So it's going to be a -1 and divide by -3. Once you have that logarithm on its own, you can flip to the equivalent exponential form. So again, that's going to be via memorization of this flip. So just sort of, if you're learning this for the first time or just need a refresher, maybe have this on hand somewhere for you to look at that conversion. That's all we're doing here. We're using that conversion to just essentially reorder the terms. And yeah, once we have x out there, it's fairly easy to see how we would get that on its own. Divide by 2, subtract 5. And that's going to give you your nice and nasty x-intercept. Y-axis intercept, a lot easier. This just is it. You just sub in your x equals 0, and there's nothing else to simplify here. That just is your closed form tech-free answer. There's no other. You're not going to get this in a tech-free. You have to get it tech-active. Endpoints, if you need them. You know, if you have like a restricted domain or such. Drop out all those key features and draw your curve to accommodate. Before I go any further, are we clear enough with how that's came to be? So one thing worth pointing out here, we had a similar issue with the exponential, which was these numbers are kind of annoying to look at. Like, you can't really tell if that's negative. You can't really tell if that's positive. How do we know? This logarithm, again, is a lot less intuitive for a lot of people, or at least I'll speak for myself, is definitely a lot less intuitive for me. It's hard to know whether that's definitely a negative number or not. Exponentials or things with indexes are a decent amount easier to analyze. So what you essentially want to do is focus your attention on the thing that you can analyze a bit easier. So knowing that E is roughly 2.7 is kind of helpful here. Because if you know it's roughly 2.7 and it's raised to the power of a third, that just means you're finding the cube root of 2.7. We don't know exactly what that is, but it's pretty small. You're then halving that already small number and then subtracting 5 from it. So even the fact that E is 2.7 and you're doing anything to it to make it smaller, the -5 is now going to become dominant. We can clearly see at this point that what we end up with is going to be a net negative number, so we draw our tick on the negative side of the x-axis. You don't even have to think about this one from here, because if you have your asymptote from here, and you know it comes from the top, it has to cut through here, and the only way this graph continues is if you then cut through the bottom. You're not going to wind it back up to try and cut through the top. That'll be a very different graph. So basically just picking your battles. Both of these numbers are kind of hard to analyze, but this one's a bit easier to look at. So after looking at that, you can now infer it's some negative number, so you draw it on the left. And this is just if you have a domain restriction, it's just mandatory for all graphs. Again, just plug in the endpoints that you have to get the corresponding y values and label them accordingly. The closed bracket is always a dark circle, the rounded bracket is always an open circle. That's it. That's all the things for the sketching of logarithms. Any questions? All right, we got like one more brief thing we can have a look at, which is logarithm solutions to exponential equations. This isn't really even new, actually. You had to do exactly this when finding your x-intercept. Yeah, x-intercept. Basically, you would get your logarithm on its own, flip to exponential, and then solve for x. It's the exact same procedure here. You have an exponential, get the exponential on its own, and then flip to logarithm instead. It's the exact same procedure of just rearranging the terms as per the conversion formula, and it's just another way we now have to solve exponential equations. Cool. Okay. So we have solving logarithms, we have sketching logarithms, and we have a new way of using logarithms to solve exponentials. Do you have any preferences on what we should start with to practice on? If not, I'm happy to pick one out. All right, probably sketching might be the best because it hits on pretty much all the skills there. You might be doing some index law stuff, log law stuff. You'll definitely be doing some conversion formulas to get your logarithm flipped to exponential and vice versa. Maybe we'll do some sketching first instead. Okay, cool. That's the thing. I'll drop in the relevant classwork doc for this one so you can see all the relevant questions and the notes. So I believe I already dropped in. Yeah, okay, let me grab the new ones. Solving sketching logarithms. The one you'll care about most will be the sketching logarithms doc that'll be uploaded shortly. So if you want to refer to that as we step through things, that'll be the doc to refer to. Okay, let's do something like this. Okay, I'll start copying down to C, and I can work from there. Y equals 2 natural log x plus 1 minus 1. I'll also leave the framework that will follow up on the screen share if you'd like to follow that instead of grab your own copy. So, what should we do to start this one? I'll give you a second to copy everything down. If you're not too sure exactly what the next step looks like, I'll even take possibilities, like ideas of what you might do.
Would you add 1 on both sides and then divide both sides by 2?
Add 1 on both sides, divide by 2. So that would start getting the logarithm on its own. That will be something that will be required. Do you know what that's heading towards? It will get us one of the steps.
Rearranging the equation so you'd have e to the power of.
Yes, that will get.
Yeah.
That will eventually get us to e to the power of. The interpret. Are you trying to interpret step 1 here? Yeah. Okay. So this step is mainly to make the logarithm equation look easier to work with. So as in, if you have a look at like the screen share, for instance, it had a bit of nastiness to it. We just wanted to make sure that we could clearly identify all the key terms in the logarithm. When you convert to exponential is more so when you start solving for those axes intercepts, because if you see getting x on its own, x is in the bracket of a logarithm. It's kind of hard to take it out of there without doing any conversion stuff. So that will be definitely part of it, getting all the flipping to exponential, but not quite yet. At least that's not what step 1's intended. Step 1's intended to just make sure that what we're looking at is easy enough to see, and this one is about as easy as you can make it. You got your dilation factor, you got your translation, and your translation. We can clearly see all the terms that matter for this one. But fair enough point. Now, let's head on to that anyway, though. So you did mention it, converting to exponential. So essentially, we're doing that when we have like our y equals 0, for instance, because that'll help us solve our x-intercept. So as you said, you'd plus 1 and divide by 2. So you have a half equals natural log x plus 1, and you would flip that to its equivalent exponential form. Do you know what that statement's now going to look like?
Would it be e to the power of a half? Or would you write the square root of e?
Either.
Okay, square root of e equals x plus 1.
Mhm.
But then would you subtract 1 from both sides?
Sure would, yeah. Square root e minus 1, and you can see we got x on its own after having done y equals 0. This has given us our x-intercept. Cool. That's one of the key features down. So we did step 4a there. You don't have to do them in order, of course. It's more just like make sure you hit these key things in some order. What else do we need to grab?
Would you find the y-intercept?
Yep, sure. How do we find y-intercepts?
Make x equals 0.
That's it. Y equals 2, natural log 0 plus 1 minus 1. This is a pretty nice nice question to pick. It does touch on a fair few things. Okay, we get it down to 2 natural log of 1 minus 1. Not a trick question. Can we simplify this further? Oh, actually it's over here. I'll have it up on the screen for some potential things you could do to simplify further. Nihal, do you have a question? Do you want to? I just noticed you went off mute.
Sorry, I didn't realize my mic was muted. So that's natural log of 1, right?
Yeah, we
Can't
have
we
natural
make
log
that a
1.
0?
Yeah, we can make it 0. Absolutely. That's one of our logarithm identities. Anytime the bracket is 1, it becomes 0. So that whole thing disappears. Were you were you saying things the whole time? Oh no.
No.
Oh, okay, cool. Thank God. Definitely wasn't ignoring you. Cool. Okay, so that gives us our y-intercept. Awesome. Yeah, we got our x-intercept, we got our y-intercept. I'll pull up the framework again. Cool. All right, we've done all the step 4 stuff. What else? There's one more key feature that we need for sketching this.
Do we need to find the vertical asymptote?
Yeah. Yeah, we're looking for that asymptote. How are we going to grab that?
We look at the translation.
That's it. So based on the translation, what's our asymptote going to be?
Is it -1?
It's going to be -1. Yeah. Now, this will matter. Why did you say x equals -1?
Because in the brackets it's x plus 1, so
Mm-hmm.
plus 1. Because it's plus 1, it's going to be -1.
That's it. Yeah, that's a shift left. Just wanted to make sure you weren't looking at this one instead. Yeah, so looking at that term specifically is the one that matters there. Yeah, that's all the key features. So we can now start dotting all that out. Or I guess you could also dot it out as you solve them. So you have your -1, asymptotes are always your dotted lines. We got our y equals -1, and we got our x equals root e minus 1. Now, root e minus 1, that's getting tough to approximate. Is that going to be a positive or a negative number?
Is it negative?
Is it negative? Why is it negative?
Because e is small as is.
Yeah, so e is small. It's 2.7 to be more specific. So when you root 2.7, the question you have to ask yourself is the root of 2.7 less than or more than -1? Like if you think about hypothetical numbers that could multiply up to give
Is it
2.7.
more than?
Yeah, it's going to be a little bit more than. Because any number that is exactly 1 would just be 1 times 1 is 1. That's obviously not going to get us there. So we need to pick a number that's slightly bigger than 1 to make that happen. So yeah, if e was anything like really, really small, then yeah, -1 would be dominant. But because e is 2.7, we use that in our approximation. And so yeah, we're now going to label this as a slightly positive number, so it's going to be root e minus 1. Now, you didn't necessarily have to approximate that. I just wanted to test to see if you guys could. The reason why is because we had an easy known number here. Like we just knew this was -1. So as long as we know the shape of what our logarithm should look like, and we know it's going to come through here, depending on if it starts, like for instance, if it starts at the top, then we know our x-intercept has to be over here. If it starts at the, why didn't that get rid of it? If it starts at the bottom instead, well, then we know the only way that's going to work is if it cuts through on the positive side. So that kind of gives away the shape. If you do your approximation and you have 2 known points, you get the shape really easily. Alternatively, if you have one easy known point and you know the shape, you would know the shape based on the base and the presence of any negative terms in there. So for instance, base e is the regular logarithm. The regular goes from bottom to top right, and because there's no negatives in there, it's not going to change it. So looking at that, you would know that it does that sort of shape. Because it cuts through here, it has to also cut over on this positive side. So you've got a lot of options basically that you can sort of pick and choose based on what seems appropriate for the job at hand. Any questions as to how any of that's came to be? This was a pretty decent one. We got to play a bit with the flipping between exponential and logarithm. We got to play obviously with the exponentials. Obviously with the graphing of it itself, and a bit of log law stuff as well. Nice. That's a sketch. Good news is I don't believe those get any tougher. Like if you pop back over to the screen share, for instance, I picked one from 2C, and that's pretty much the most involved that there is. That's the one that's got the most terms on it. Like, yes, there's negatives, but you can see all of these have a base of e or a base of 10, base of 2. These are all bases that are greater than 1, so you never have to really worry too much about the 0 to 1 base stuff. Do they even touch on it at all? Anyway, that's a sidetrack. It's worth pointing out, but it seems like they don't actually do any questions on it. There is a bit of transformation related stuff in here. It's so rare to actually show up. It's not appeared on an exam, but I have a suspicion it might be a sneaky little sack thing. I have yet to write a thing about it, so maybe this is a good time to start talking about it. So this, if it's going to show up anywhere, will show up in a transformation section in a sack. Here's how it works. So we kind of talked about how exponentials and logarithms have this additional transformation term, if you want to think about it, which is the base. The base has a decent impact on the shape of the graph. We know how to work with dilations, translations, reflections, even inverse transformations is one thing we didn't quite touch on in any of our classes just yet. That's the flipping of the x and the y. But how we're going to handle things with different bases. The way you do it is with your index law stuff. And what you'll notice is this is one that I previously thought as a niche example of using your index law. So because these guys have two separate bases, it makes it very hard to compare them to each other. So one of the things you want to do is try to figure out how can I rewrite this to have the same base? What can I do to especially from the 2 to the x, make it look like e to the x, because you want to figure out what transformation gets us from 2 to the x to e to the x. What you do, oh, they actually did it backwards a little bit. They started with e and made it a base of 2. That's kind of a bit backwards, but I guess that's the example we have. Sure. So the premise was you essentially take the number that you want to convert and then use the last of the index identity, the logarithm identities, to convert it to an equivalent thing with a new base that you want. So to point out the one that they're using this, but instead of starting with that, they're starting with the number they want and then choosing the base. It's kind of nice. It's a new take on this thing, where kind of like with logarithms, you could take an initial logarithm and convert its base like this. You can take an exponential, or any number for that matter, and choose a base as an equivalent. So basically, they started with the number they wanted to have, or they already had rather, which is e. That's this bit here. And then they chose their base such that it was directly comparable. So, in other words, 2. So basically they looked at this other side of the equation, this a term, and they set that as 2, just because you can choose what you want to put in that spot. And as long as you make sure that e goes in the bracket there, because the left-hand and right-hand side has to be the same value, this is an equivalent statement. You've satisfied both sides of the equation there. So if e is the same thing as that, then you can replace this e with this equivalence. E to the x now becomes this, and using your index laws, you can now rewrite it like that, just distributing that x through the power. Why do you do that? Well, what you end up with is 2 separate things with 2 to the power of x in them. The only difference is this one has a dilation factor applied to it. So you've done some math magic to flip it from being some weird base transformation to now in terms of things we can actually talk about when it comes to transformations. This is definitely a dilation factor. It's a multiplication on the x. Now, remember again, x dilations have to appear as divisions. So the fact that isn't log 2e, it's 1 over log 2e, because it's always got to appear as a division for the x stuff specifically. A lot of nuances in that one. It's a cheeky little thing. It hasn't shown up on any exam ever. It might be a nice, it might be like a tricky sack thing that they'll put 1 mark on. And it'll be like a separator question. It was just a cool thing I found in the book as I was putting together the classwork doc for this one. It's a weird thing. Is there anything to clarify further on that? I'm sure there might be. There's 2 examples of it down here. Maybe we'll just make sure that we can do it. Let's have a look at question 6. We'll see if we can do it together. So we want to go from y equals 3 to the x, and we want to convert it to y equals e to the x. And what I'll do is I'll write, just so we can all have it on the same page, the thing that we should be using, which is ax is equal to x. That statement will help us with our thing, and I'll even have the example up as well if you want to just directly compare to that. Cool. When you're settled, does anyone want to take a stab at how we're going to get from left to right? So if you take a look back at the example, the first step, if we think about it high level, was they looked at the exponential they're going towards. Specifically, they looked at the base of it, and they tried to convert it into something that was more easily comparable to the starting base. So they had e and 2 they were working with. We have e and 3 that we're working with. So based on that, what do you think step 1 might be? So it'll be a pretty good skill for you to learn in your studies as well. Not necessarily this example, but being able to look at an example that's worked and then infer the steps from it and apply to a similar looking question is definitely a skill worth building. So I feel like even if you guys do get this wrong, you may or may not, it's a skill worth developing. So I think we should spend some time on it. Anyone want to make a wrong guess and see how we go?
Do we add a common power on both sides?
Have a common power on both sides. Yeah, so we would like to have some more commonality between the two equations. Any ideas how you might go about that?
We can raise both of them to the same power, both sides.
Raise both to the same power. Well, the power would be x in both of these cases. So currently they have the same power already, technically. The difference would be the base, if that's what you meant.
I'm just inferring it from the example.
Yeah, okay. So what do they do here in the first case? So they basically, if you look at that example again, they had a graph they're starting with, a graph they're ending on, and the first thing they said was do this. Now, that's not particularly helpful. We give reasons why we're doing things, ideally, but what they're looking at is the only spot where an E would exist is in here. So something about the base of this new one is what they're targeting. And they're doing some sort of conversion to it, which might be a bit hard to see immediately because they're not explaining anything really. But what they're doing is the thing that I've written out in red, that log identity. What they're saying is the base that we end up on is different to the base we started with. So we're going to do some sort of conversion to it. We have this E, and I want to rewrite that into a base that's more convertible. And I can do that with this logarithm statement, if you're looking back at the handwritten notes bit. So by plugging in E as X, all I need to do now is fill out the rest of the statement with whatever this A is. Now the good news is A, we can actually choose to be whatever we want. And so what we're going to end up doing is realizing that because A is a base, well, it's base in both the log and in the exponent, we can now choose that as 3 in this case because that will make it match the thing we want to actually have. So we choose a base of 3 to do this conversion. So we now know that any instance of E is now the same thing as that. You know, this could be 4, 5, 6, whatever, but we're going to choose 3 because it's more comparable. So this instance of E over here now becomes y equals 3 to the power of log 3e. And since that was e, it's also raised to the power of x. That bit there is just substitution. Are we clear enough on what's going on there? That's like by far the key step of this. Cool. The rest of this is stuff you guys know how to do now. So using your index laws, you can distribute the power through. might look a bit weird because you've got logarithms in the power, but it is technically stuff you've done. This is still fundamentally just a coefficient. This is where you're ending. This is where you're starting. You start with no dilation factor. You ended with a dilation factor. So to get from here to here, you have to put this in there. Now, the slight nuance on it is that dilation factors that are affecting the x, the actual factor itself needs to appear as a division. So you would specifically say this is 1 over log 3e as the factor that you would mention. I'll bring up the if you guys still have time for it, I'll bring up the what that looks like in the transformations doc just so you can see what I'm referring to as to why we would do it that way instead of just saying log 3e. Actually, I'll even show the proof as to why, just as a refresher. Cool. So if you have a look back at the screen share, this is how we apply any transformation using our point form. Essentially, what this looks like is dilation factor is always multiplication on a variable. Dilation factors that are in the x direction are multiplied on the x. But as part of the sequence of transformation stuff that we do, the steps are as follows. You start with the thing you want to do, but to put it into an actual function, we have to process it a little bit. And we do that by starting with getting the x and the y on its own, which in this case means dividing both sides by a, and then you can sub that into the function that you're trying to apply that transformation to. And because you've done this flip to get the x on its own so that it can be subbed into a function, remember functions work on x and y, not x dash and y dash. That's why you have to do that rearranging, so you can sub it in here. It ends up in the division spot rather than the multiplication spot. And so because we had it in the multiplication spot, we'd have to do a little bit of a flip to make the factor actually observable. Cool. We covered a fair bit today, so if there's anything that I can clarify further, happy to do so. We have hit time, so if there's no further questions, I'll let you enjoy the rest of your days. We'll recap this in Friday as well.
Thank you.
No worries.
Have a good day.
You too, mate. Take care.